All right, we are going to work on 8.5, which is solving exponential equations. 2 learning targets that you can solve exponential and logarithmic equations. Okay, some basic properties. Let's say we have b as a positive real number and it's not 1. Then b to the x power is going to be equal to b to the y power only if those exponents are the same, right? So only if x and y are the same. So for example, here, if I have 3 to the x power, and I know it's equal to 3 to the 5th power, well, since I have the same base, I know that my exponents are going to have to be equal to each other. So in this situation, this exponent should be equal to this one. Okay, so in this case, it would be then x is equal to 5 if, only if the x is equal to 5. Okay, so we can use that property to solve some pretty simple basic exponential equations. Okay, so here I'm looking at example number 1. Okay, so example number 1 says that 100 to the x power is equal to 1/10 to the x minus 3 power. So as I'm looking at this, okay, I can look at, and I don't have the same base, right? I have a base of 100 and I have a base of 1/10. Okay, but the thing that's nice about this, though, is 100 and 1/10 all are a form of 10, right? 10 squared is 100, and 10 to the negative first power is 1 over 10. So that means we can probably do some rewriting here to get myself to have the same base like I did up here in this first example here, and then I can use that to solve. So for example, I know that 100 is equal to 10 to the 2nd power. Okay, that's equal to 100. And then I also know that 1/10 is equal to 10 to the negative 1st power. So as I look at this, I can just rewrite 100 as 10 to the 2nd power. Okay, so let's go ahead and do that. So I'm going to have 10 to the 2nd power, but then I also have this now that 100 is raised to the x power. Okay, and so we're going to have to figure out a way to simplify that, but we should probably finish writing our equation, and I know that 1/10 is going to be the same as 10 to the negative 1st power, but that's all being raised to the x minus 3 power. So we need to look and ask ourselves, like, how can I simplify this so I just have my base 10 raised to an exponent instead of having powers to powers? Okay, so you're going to have to think back to previous chapters about how we are going to simplify this. Specifically, what is our exponent property when I have a power to a power? Okay, so hopefully at this point you've already identified that having one power raised to a 2nd power, you end up multiplying those. So 2 times x is 2x. So now I have 10 to the 2x power is going to be equal to, and then here again I would have to multiply. Okay, negative 1 times x minus 3 together. So you're going to have to multiply x minus 3 all by negative 1. Okay, so then this is going to get to 10 to the negative x plus 3. Okay, and that's what's remaining if I go negative 1 times x minus 3. Now I have it in this form, just like this property. I have a common base raised to an exponent. Okay, and so this ends up being extremely helpful because then I don't even really have to think about the base anymore. I just know that the exponents have to be equal to each other. I know that 2x is going to need to be equal to the opposite of x plus 3. Okay, and then this just becomes just a standard equation for us to solve. I can add x to each side to get 3x is equal to 3. And since 3x is equal to 3, 3 times x, I can divide by 3 to isolate my variable and find out that x is just equal to 1. Okay. So when the base is not the same, so like sometimes you might just have a pretty basic problem like up here where you just have to set them equal to each other right off the bat. But when they're not equal to each other, you might want to look and see if they can be rewritten in a form where they would have the same base. Okay, so let's look at 2. Okay, so the first thing when I'm looking at these problems, I want to look and ask myself, like, can these numbers be rewritten to have the same base? So I have 2 to the x power, and it's equal to 7. So you want to look at the 2 to the x power, right? 2 really can't be rewritten as a different base, and then we want to ask whether 7 can be rewritten as a different base. Well, I know 8 can, because 8 can be rewritten as 2 to the 3rd power, but it doesn't seem to me that 7 can be rewritten. And this is where what we worked on in the previous couple sections becomes incredibly helpful: logarithms. Okay, because I know raising something to a power is going to undo if I take each side to that same base or logarithm. Okay, so what I can really do here is I can take each side to the log base 2. Okay, and I'm taking log base 2. Okay, I'm taking log base 2 and not 7 because my exponent is on the base of a positive 2. So when I'm taking log base 2, I'm doing that so I can undo this work here and just remain with this exponent here. Okay, these are inverses of each other. We worked on that in, I believe, 8.3. So I can just rewrite this as just x now. Okay, this is going to be equal to log base 2 of 7. Okay, so now this is actually right here. This is actually my exact answer. Okay, like very precise. There's no rounding. This is exactly what it's equal to. It's equal to log base 2 of 7. Okay, but a lot of times we a decimal approximation really helps us think about it more. So we can go ahead and get that decimal approximation. But you're going to have to remember our change of base formulas. Okay, so we did some change of base formulas in 8.4. And really, like I said, what it's going to be most helpful for us is to be able to get our answers out of the calculator. Okay, so I can take any logarithm with a different base and a number, and I can just take log base 10 is the one that we're going to most typically use. We can take log base 10 of A and divide it by log base 10 of C. Okay, so we're going to go ahead and do that. We know that the change of base formula says that I can say that this is equal to log base 10 of 7 divided by log base 10 of 2. Okay, and so then now the log base 10 of 7 is something that we can just throw into our calculator quite easily. Okay, log base 10 of 2 is also something we can do. So let's go ahead and take the time to do that here. Okay, it's going to actually be no different than our previous section. So I can just go ahead and hit whenever I have log and there's no base number below, it's implied that that's base 10. So I can have log base 7 or base 10 of 7 divided by log base 10 of 2. Okay, and what this is going to do is give me about 2.807. Let's go to 3 decimals, let's say. Okay, so then this is equal to approximately 2.807. Okay, so what is this telling me? Okay, so this is telling me that when I raise 2 to the 2.807 power, okay, I am going to get 7, okay, approximately 2.807. So let's just go ahead and test that. I think we've done a little bit of this before. So I'm going to take 2 to the 2.807 power, okay, and as you can see, it's 6.998. That would round up to 7. But why am I not getting exactly 7? Well, why am I not getting exactly 7? It's because I'm not plugging in this exact number here. Okay, I'm plugging in a rounded version because 2.807354922 blah 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 is not the same as 2.807. They're great approximations for each other, but they're not the same number. Okay, so these are just some exponential equations that we would be expecting you all to be able to solve. Okay, so why don't you all take the time, pause the video, try A and B on your own. They're very similar. okay, and then check your work with mine here in a moment. All right, so I'm assuming that we've already tried A and B, and you're just here to check your work and see how you're doing. Okay, so let's go ahead and dive into this. Okay, so here I'm looking at A, and I have 81 to the x power and 1/9 to the x plus 3 power. As I look at 81 and as I look at 9, I can kind of think to myself that I know both of these numbers are powers of 9. Specifically, I know that 81 is equal to 9 squared. And that 1/9 is equal to 9 to the negative first power. Okay, and this is just from previous sections dating back to 8th grade Algebra 1. Okay, just some exponent properties. Okay, so we can rewrite this equation. Instead of 81, I'm going to rewrite 81 in a form that's equivalent. I'm going to rewrite it as 9 squared. So I'm going to say that 9 squared raised to the x power is going to be equal to, and again, instead of 1/9 here, I'm going to write 9 to the negative first power. They're equal to each other, so I can just simply replace them. Okay, so then this is going to get me 9 to the 2x power. It's going to be equal to 9 to the negative x minus 3 power. Okay, so again, 2 times x is 2x, and negative 1 times x minus 3 is the opposite of x minus 3. Okay, so then at this point here, again, we don't even really need to concern ourselves about those bases anymore, because I know that since the bases are the same, the exponents are going to have to be the same if they're going to be equal. So I need to know that 2x is going to be equal to the opposite of x minus 3, and then just do some algebra to solve. Okay, in this one, I happen to get that 3x is equal to negative 3, and then when I divide by 3, I know that x is going to be equal to negative 1. Okay, so even though that these problems are kind of lined up nice and neat for you, you want to be thinking about, like, what method am I going to solve? Do I need to use a logarithm, or do I need to rewrite the base in a form to make them equal to each other? These are the things you all need to be thinking about as you're working through these problems. Okay, so the next one, 3 to the x power is equal to 8. Okay, so as I'm looking at these, I want to know whether or not I can rewrite 3 and 8 so that they have the exact same base. So 3 to the x power, so 3 is really just only a power of 3. It's not a perfect cube or square or fourth power or anything like that. And so 8, you want to see if you can rewrite 8. Well, you could rewrite 8 as 2 to the third power, but then I have a base of 3 and a base of 2. And that's not what we're looking for. So to me, it really is striking me that we really can't rewrite 8 as a base of 3. So we're going to have to use logarithms here. So I'm going to have to take log base what? You all should be thinking about what base logarithm should we be taking to get that variable isolated. Okay, this one you should be taking log base 3, okay, of 3 to the x power, because when I take log base 3 to each side, I have base 3 here. These are going to undo each other, and now I'm just left over with whatever this exponent is. So x is equal to log base 3 of 8. Okay, again, this is my exact answer, but I would like a decimal approximation. Kind of helps me think about what power. And in my mind, I know that this should be a little bit less than 1, because 3 to the second power is 9. 8's a little bit less than 9, so the second should be a little bit less than the second power. So we have all these problem-solving skills we can think about to kind of reason our way through. Okay, so we're going to have to use the change of base formula to be able to get the x proper decimal approximation. So we're going to take x is equal to the log base 10 of 8 divided by log base 10 of 3. Okay, so let's go ahead and use the calculator to find that. So I'm going to take log base 10 of 8. I'm going to divide it by log base 10 of 3. Okay, and I'm going to get that x is going to be approximately 1.893 because the 7 would round that 2 up to a 3. So that's my decimal approximation. Okay, so I can take 3 to the, and if you recall, I can hit second, and then the negative number sign, and then that will give me my previous answer. And I don't want to plus anything, and when I hit enter, it is that. So when I take 3 to that power, it is going to give me 8. Okay. All right. So we are going to just solve some basic exponential models here. So we are cooking alchia, an Ethiopian stew. And when you take it off the stove, its temperature is 212 degrees Fahrenheit. The room is 70 degrees Fahrenheit, and the cooling rate of the stew is 0.046. How long will it take the stew to cover, or the stew to cool the stew to a serving temperature of 100 degrees? Okay, so it looks like here we know that the temperature we're trying to get to is 100 degrees. So here we have this formula here to work with. So T is probably the number that we are trying to get to. So we have 100 is equal to T naught. So anytime you're going to see T naught, that anything naught tends to be initial. And so I'm going to take the initial, which is 212, minus the temperature of the room, which is T sub R, raised to the e to the negative 0.046 T, all right, plus 70. Okay, so let's just go ahead and do some simplifying. Okay, first I'm going to subtract 70 from each side so I can just get this all by itself. So I got 30 is equal to, let's go ahead and get 212 minus 70, which is 142. Is raised to e to the negative 0.046 T. Okay, and so when you're solving problems like this, you know, we really need to, you really want to get like the base that's being raised to the exponent isolated. So in this situation, we have 142 times e to the negative 0.046 T. So if you wanted to get that by itself, you would divide by 142. Okay, so we can go ahead and get 30 divided by 142. That's a pretty messy decimal, and I really don't want to round. I really only want to have to round one time, and that's at the very end of a problem. So let's go ahead and simplify that fraction to 15 over 71. And that's going to be equal to e to the negative 0.046 T. Okay, so now as I'm looking at this, I need to just get this. You know, it's hard for me to solve, you know, problems where the variable's in the exponent, okay? So let's think about what's going to undo that e to the, okay? Because if we could get rid of that, then we might just have like a regular problem to solve, okay? And as I'm looking at this, I have 15 over 71 e to the. So, you know, if we kind of look back at our previous page, you know, I know taking 9 to the power of something, or rather a better example, if I'm taking 2 to the power of something, I'm going to use log base 2. Or if I'm taking something to 3 to the power, we're going to use log base 3. So this one, what's our base? Our base is e. So when I have a base of e, you need to think about what logarithm is going to undo that. Okay, and hopefully you've already identified that it is the natural logarithm. So I can take the natural logarithm of 15 over 71 is equal to the natural logarithm of e to the negative 0.046 T. Okay, and so then what's going to happen is this is just going to be a number, Okay, and then these are going to undo each other, and all that's going to be left is the exponent. Okay, let's go ahead and check to see if the natural log of our previous answer here is, that's still a decimal, and I really don't want to round until the end. Okay, so let's go ahead and just leave this as natural log of 15 over 71. And it's going to be equal to, well, these undo each other, so I have negative 0.046t. And just have to get the t by itself and divide. Okay, so we're kind of running a little bit out of space here, but we're almost done. So we know that here's our exact answer, actually, is the natural log of 15 over 71 divided by negative 0.046. Okay, that's pretty messy. Let's actually figure out what it is. Okay, so let's get the calculator out. We're going to take the natural log of 15 over 71, and then we're going to divide it by negative 0.046. And about 33.796. Okay, so 33.796. Okay, so how long will it take? It is going to take 33.796, and it doesn't really give us a unit, but kind of based on 33, I'm inclined to think that it's minutes. But whatever unit of time this is in, this is going to be our answer here. I'm pretty confident that this is probably minutes. Okay, so you might run across a word problem or two that has kind of has a formula for you, but this is just a nice use of like where we're going to see stuff like this and how it might be used. So here, it's also no coincidence. It's actually quite common that you're seeing E in this thing that's talking about temperature cooling, because E is the natural logarithm. It's the rate at which things like exponentially grow or decay in nature. Okay, so this is a great example of seeing that. Okay, so moving on to logarithmic equations. All right, so if b, x, and y are positive real numbers, but b is not 1, we know that if I take log base b of x is equal to log base b of y, if and only if x and y are equal to each other. Okay, so this one has a lot more stuff kind of going on to it, but really it's fundamentally the same as this previous example where we talked about, well, if I have the same base and it's raised to an exponent, those bases are going to be equal, or those exponents have to be equal to each other. So if I have two logarithms and the base of the logarithms are the same, that means like the inside logarithms of are going to have to be equal to each other. Okay, so log base 2 of x is equal to log base 2 of 7. Then that means that x is going to have to equal to 7. And furthermore, if x is equal to 7, then log base 2 of x is equal to log base 2 of 7. Okay. Okay, so logarithmic equations are equations that involve logarithms of variable expressions. Okay, so let's go ahead and solve these problems. Okay, so as I am looking at these problems, okay, I have the natural log of 4x minus 7 is equal to the natural log of x plus 5. Okay, so you're often going to see parentheses around like what's being taken to the natural log if it's an expression. So like here you don't see parentheses around the x, though you could put the parentheses around the x. Okay, so but I know that I'm taking the same base of the logarithm, and it's base e, and they're both equal to each other, so that just means these inside parts have to be equal to each other. Okay, I know that the inside parts are going to have to be equal to each other because it's both logarithms with the same base e, in this example. Okay, so I'm going to subtract x. 3x minus 7 is equal to 5. Okay, then I'm going to add 7 to each side here to get 3x is equal to 5, and 7 is 12. And then divide by 3. And as always, you can go through and check your work here. So I know that the natural log, I'm sorry, folks. Okay, 4 times 4 minus 7 is like 2.197. And the natural log, 4 plus 5. So we had to have made a little bit of a mistake here. 4x minus, oh, and if you can see when I plugged it in, I went natural log here, and this is log base 10. So let's actually try the natural log. 4 plus 5. And then we get that same number. Okay, so a problem like 4, I'm hoping really won't give you too much pause, that you can just go ahead and, when the bases are the same for the logarithms, you can just set them equal to each other. Okay, let's do number 5. Number 5 is log base 2 of 5x minus 17 is equal to 3. So as I look at this problem, I've log base 2. And so, as I look at the previous examples that we've done, I kind of knew that these were inverses of each other. So if I have 3 to the x power, I can take everything to log base 3, and they undo each other, and I'm just left over with what's on the inside. This problem is going to be quite just the opposite of that. This one I have a logarithm with base 2. So what I'm going to do is I'm going to take 2 to the same power. I'm going to take everything to the power, or 2 to these powers here. So I'm going to take 2 to the log base 2 of 5x minus 17 is going to be equal to 2 to the third power. Okay, now what's going to happen is very similar. Our 2 to the 2 to this, and our base of 2 and our logarithm base 2 are going to undo each other. So what's left over is just this 5x minus 17. And 2 to the third power is 8. And then now this is just a problem I can solve. So this is 5x is equal to, so 8 plus 17, so 17 and 3 is 20, and then another 5 would be 25, and then divide by 5. Okay, and again, if I wanted to, I can go ahead and check this out. This one would require us to use a change of base formula, which we can do just to check our work if we want to. So 5 times 5 minus 17, that's 25, minus 17, and that's 8. So, okay, so I can say that this is log base 10 of 8 divided by log base 10 of 2. Log base 10 divided by log base 10 of 2. And as you can see, that is equal to 3, which is what we wanted it to be. Alrighty. One more page, and we are done. Okay. So, using the previous problems that we just did, I want you to go ahead, pause the video, and try these ones, D and E, please. Okay, so we're under the assumption that that you all have actually already paused the video here, and knowing that, we are going to dive into this so you can check your work. Okay, these ones have the same base of E. So since these have the same base of E, I can just go ahead and set the parts equal to each other. Okay, and so then I'm going to subtract x. Okay, 4x plus 2 is equal to 10. Subtract 2. And this one, x happens to be equal to 2. Okay, this one has log base 3. So I'm going to take everything to 3 to the power of each of these parts. And this can be equal to 3 to the 4th power. Okay, so These are going to undo each other, so now I'm just left over with 10x minus 9 is equal to 3 to the 4th power. I don't happen to know that off the top of my head, so 3 to the 4th power just happens to be 81. Alrighty, and then I can add 9 to get 10x is equal to 90. And this is just 9. Okay. So there's D and E for you. Go ahead. Hopefully that you did pretty well on these because I am moving